see. Live, we're live. Good. Okay, everybody. I don't have a view of the stream, so I'm not sure how many people are with me today. But regardless, this stream will be uploaded to YouTube later, so you're all good. And today we're gonna solve this problem. You're given n numbers as well as n probabilities that sum up to 1. Write a function that to generate one of these numbers with its corresponding probability. And here's an example. If you give 1, 2, 3, and 4, 0 0.1, 0 0.5, 0.2, 0.2. Okay, right? And it's given that we can generate numbers uniformly. So let's kind of just shim that in. Random. And let's say that uniform is random functors partial random dot uniform 0 1. Okay, so this basically gives us what we were supposed to already had. Because this is not an actual interview, we have to build it ourselves. As you can see, this gives us numbers between 0 and 1, so we're good, right? We have what it takes. And just to kind of again copy like the thing we need. 1, 2, 3, 4. And probabilities 0 0.1, 0 0.5, 0 0.2, 0 0.2. Good. Okay, so now we have, and now, so as always, I first like to get the shape of the function right. So numbers, probabilities. And for now, we'll just return the first one. Alright, so this is just the shape of the function, but that will let us already kind of play with it and see that the shape is right. Alright, so numbers, probabilities, generate with probability. Okay. Right, and yes, it's always gonna return a 1 because, okay, but that means we got the function right. And clearly we need to use this function, right? Like Chekhov's gun, right? You give us this thing, we have to use it. So, and the only thing we can do is call it. So, wait, we'll call it wait, or we'll call it wait for now, and we will find a better name later. Uniform, and we'll still generate the first one. Okay, so now the naive algorithm is pretty simple. Right, so we'll do while wait. No, we do this for value probability in probabilities if prob greater than wait. Let's do it doesn't really matter. I'm kind of trying to think what's the cleanest way. No, I want this. Wait. Yeah, that's probably good. If probability greater than wait, return value. Otherwise, wait minus equals probability, and then we should never get here. If we got here, right, so you notice that all these numbers sum to 1. And uniform always has to be less than 1. So raise value error greater than 1, and we'll give the last weight. So this is mostly as defensive coding because this should never return something it's one or bigger, but in case we made a mistake. And of course this needs to be zip numbers probabilities. And if we run it again, and that's kind of, so let's do this. Import collections, C equals collections counter. Now I don't remember the right method, but for let's do this 1,000. So let's kind of generate 1,000 of those and see what it gives us. Update, ploop, ploop. Help C. So I thought it wasn't update. I guess we can just sorry about that. We can just do that. Okay, and let's now do C. So you see that 2 is about 500, is about half. 3 is about 200, 4 is about 200, and 1 is 100, right? So that's at least like anecdotal evidence that I'm actually generating something with the right probabilities. So what's the problem here, right? So there is no problem per se, but as always, your interviewer is gonna be annoying. I'm gonna be annoying if I'm the interviewer, but this is kind of standard practice for interviews, whether you like it or not. They're gonna say that's good. How long does it take? So you go, Well, on average, right, we'll go through around half of the numbers here. Right, so that means that it's O of n, right? So I'm looping over the numbers, and then can you make it faster? And I'll be like, I don't know. So can we make it faster? That is a question before us. And the answer is of course yes, but we have to do pre-calculation with that. So let's kind of do like pre-calculation, and we'll take probabilities and we'll generate accumulated probabilities. So def under do, we'll give it a better name maybe later, but for now I just want to get the basic shape right. Val equals 0. For x in weight in probabilities, val plus equals weight, yield val. do return list of do. Okay, so let's see what that takes. So pre-calculate. If we give it the probabilities we got, so it's the same thing except now we accumulate, right? So we don't give the probability that this is a number. We give the probability that the number is lower than. And you'll notice that by definition, since probabilities are always positive, or at least non-negative, this list is obviously can be any order, right? Like 4 had a low probability, 1 had a low probability, but 2 had a high probability, right? There's no ordering here. You notice that the probability that it's less than a certain number, right, is of course strictly increasing, because it's more probable that you're going to be less than 3 than it is that you're going to be probable less than 2, because if you're less than 2, you're definitely less than 3. Okay, so we'll call it less than probability. And now we import a delightful little model called bisect. And of course I haven't used bisect in a while, so let's read up the help. And there's bisect left and bisect right, and I think we need bisect left. And the reason we need bisect left is because we did yield val here, and of course we could have chosen to do yield val here, right? And so let's kind of see what happens if we do that. I'm gonna return it because I like the other conventions better, but just 1 second. Hi Jennifer, as I told you, I am streaming right now, so literally everybody in the world has seen your message. So let's talk later. Bye. Yep, sorry about that. Okay, so yes, this is the other convention, right? Which start with 0 and then with 0.8. And with this convention that I think is, so it's like strictly less versus less or equal to. That's a more convenient convention, but that means we do bisect left. And we're not going to insert, of course, the number, but let's see what happens when you do bisect dot bisect left. And let's see what happens when we do 0.5 and the list, so less than probabilities. Did we make a mistake? I think we changed the order. Bisect dot bisect left. Yes. We did the wrong order. So this is why it's good to write a little practice with a known number. 1, right? Because the index will be 1. Now if I had 0, 5, then it would be 0. Right? So you can see that it basically tells you which one. Okay? And now the nice thing is that if you do this, and we'll call it with LT probability, and we'll call this variable LT probabilities. Then now all we need to do is just do bisect left LT probabilities. Wait. Bloop, bloop, bloop. Okay, so that's IDX. And now we just do return number of IDX. And this is like again gonna return some weird stuff. I think if it's bigger than 1, I'll just return the last element, which is fine. I don't really care what it returns. I think that'll be an index error, so that's fine. I'll still raise an exception. And now let's see if it still does the right thing. So we'll again kind of generate with LT, and here we need to give less than probabilities. Generate with LT. That's not, oh, because I missed an underscore. Okay, good. And now if we do C, again, you see that 2 is about 5, right? Again, like let's put the probabilities again here. Right, so 2 is about 5, right? And 4 is about 200. 1 is again about 100. 3 is slightly off, but again, that it's all probabilistic, right? So if we run it again, you'll see that it's less, and we can obviously run it for a little bigger and kind of average things out a bit more. Right, so now you see that it's even closer. This is close to half, this is close to 2000, 2000, 1000, right? So we still have the same overall probabilities. But now, if you look at bisect left, right, you'll see that it's O of log, right? It doesn't need to check everything. But of course, computing the lesson probabilities pre-calculate still takes O of n. We still have to go over all the elements here, right? So when we talk to the interviewer, of course, we make it very clear. I can do O of n pre-calculation that I can cache or do all kinds of tricks with caching, and if I get it reused with the same probabilities, even if it's, by the way, with different numbers, right? So we can be pretty fancy with caching, but I don't want to get into like fancy automatic caching. In general, usually you want to be explicit about these things anyway. Then we can pre-calculate the probabilities like this. We'll get the lesson probabilities, and then we can use bisect. Again, if your interviewer is kind of an annoying person, and again, I don't promise exactly how annoying your interviewer will be, but they can be extremely annoying, and they say, well, can you implement bisect left to make sure that it really is O of log n? Then let's implement our own bisect left, and then we'll kind of remove this bisect that. Okay, so bisect left and array and x. We don't need the high and low because for our purposes anyway, it doesn't matter. Low 0 equals 0, high equals len of x minus 1, and midpoint equals low plus high divided by 2, and we'll do this while low is less than high. I want this division. While high minus low is greater than 1. And now we do this. If mid is less than x, then clearly we're above the midpoint, right? So we can assume that low is mid. This should probably be inside the loop. Bloop, bloop, bloop. If mid is greater than x, then high equals midpoint, right? Because at this point we know that mid is above x, and else, right, which means mid is equal to x, right? And remember, we want to return else break. So when we break, we know that array of low is less or equal to x. So we can do return low. And let's check some bisections. So let's do bisect left, LT, how did we get it? Less than probabilities. Less than probabilities, and let's do first 0.1. So this should return 0. Object of type float has no len. First, this should be array of mid, and array of mid, of course, and of course it's the len of the array, not of x, and that should work. Yep. And if we look for this, so this is wrong, right? Because so should we return high here? But then, okay. Yeah, no, I think I made a mistake. Let's just do this. Let's not do early breakage. And then you can just make it an else. And still return low. Okay, so this is wrong, right? Okay, let's debug it then. Then probabilities. Let's print it out so we can see what's going on here. Okay, so clearly it should have returned 1. Because we needed to, okay. So while high minus low, and let's kind of print both high and low here. So mid, should I just return mid? No, I don't think so. Yeah, it's not gonna help us much. Yeah, okay, so let's figure out what's going on here. While high minus low is greater than 1, let's print high low here. Okay, should have gone one more through the loop, right? No, because it's already 1 0. Okay, so let's figure it out. This if r of low so we if we reach that point, low and high are the only candidates, so we have to get one of them. Maybe it's the other way around. Yeah, it's the other way around. If x is already lower, with low return low, otherwise return high. Okay. This is still 0, but if we do 2, excellent, and we can remove the print here. And now let's copy this function and remove the bisect. So now we're using our own bisect left. And let's do this. Toop toop. And again, if you look at the probabilities, then 2 is about half, 4 is about 0.2, 3 is about 0.2, 1 is about 0.1. So we got the code right. So this is how you implement. This is, of course, high-low, right, or binary search, or bisection search. There's all kind of names for this algorithm. It's a very straightforward algorithm, except it's always annoying to kind of deal with the corner cases, which is why careful debugging is required. And you saw how I was careful to tie out all the options. Sorry. Anyway, so this is how you solve the problem, right? Like, we finally got to a solution where if we do the pre-calculation and we implement our own bisection, then the actual code to do that is 3 lines of code, right? We moved all the code out to a helper function that we wrote. So this is it. This is how you would solve the problem. I highly do recommend doing it in a real interview like I did. Like we literally say, okay, let's do it the simplest way possible. Let's see what it takes. And then you can even kind of be straightforward about it and say, hey, this is O of n. Do you think I can do it faster? Would you like me to do it faster? And then you can talk about pre-calculation and where you would cache it and how you would cache it and talk about strategies like that. Write the actual pre-calculation code. Then you can say, well, I'm gonna use binary search. Can I use the built-in module, or would you like me to implement it myself? A reasonable interviewer will tell you use the built-in module, but your job is to pass the interview, not to make sure that your interview is reasonable. So if they tell you do not use the binary search, I say that's fine. I'm gonna write it myself. Here's how you write it. So and basically finish up. Okay, so this is how I suggest approaching this question. This is how I would approach it if I was given it in the code screen. Hopefully that was useful. If you're interested in learning more about stuff, I am giving a seminar about better unit testing that you can register for. It's on my Twitter. So hope you had fun. Enjoy.